Okay folks, welcome back to this video series. So in this playlist I'm using RStudio and the R programming language to do some basic data science tasks and statistical analyses. In the previous videos we've done some visualization, some data cleaning. In the last couple of videos we got into some null hypothesis significance tests such as the t-test and analysis of variance. So what I'm going to do in this video is just demonstrate how to conduct a simple linear regression analysis using RStudio. So we normally use linear regression to model the patterns in data using the equation for a straight line. So in its simplest form, what we'd have is we'd have a scale on numerical independent variable and a scale on our numerical dependent variable, and we'd be looking to fit a straight line to try capture the pattern or the relationship between those two variables. And what we're interested in knowing is, can we, given a particular score on the independent variable, can we predict scores on the dependent variable? Okay, so regression, linear regression in particular, probably the most common type of statistical model used in many disciplines, and particularly behavioral sciences and psychology. And the example I'm going to use today is not particularly behavioral themed, because I'm just going to use a built-in data set that comes with R. So I'm going to load the tidyverse because I'll fit some of the models using kind of pipe operators and stuff, so they're pretty useful. So I'm going to load the tidyverse. Let me get that correct. So Control and Enter. So that's worked, and you can see in the console window below it's showing you which packages it's loaded, ggplot, dplayer, things like that that we might want to use to plot and manipulate data. It's also told us where we've got some conflicts. I've explained what those mean in previous videos, so I won't get into too much detail about that. But as you know, because I've used them in some of my previous videos, R has a large number of built-in data sets. If I use the data command, if I just do data and parentheses like that, you'll see it opens this new pop-up window here, and it tells us all these different data sets that are available for our use that we can just import and analyze. So let me close that. So the one I'm going to use is called cars. It's a very small data set. Only got two variables, but they're both scale variables, which is pretty useful really for the type of analysis we're going to run. So I'm going to do head to call the first few lines of this data set, and I'm going to provide the name of the built-in data set, which is cars. And you can see, if you look in the console window, we've got two variables, speed and distance. Distance being stopping distance, I believe. So speed, maybe in miles per hour, kilometers per hour, and stopping distance, I don't know, maybe in meters, something like that. But what we're going to do is fit a linear model to see if we can, given the kind of stopping distance for a car, if we can predict sort of how fast it was going by fitting a linear regression model. Okay, so the syntax to do that in R is LM for linear model. And then in parentheses, you provide a number of particular arguments. So you provide the dependent variable, you provide a model formula, and you can see it specified here, speed and then a tilde and then dist. So they are the names of our two variables separated by this tilde, and we've seen this in a couple of previous videos. These model formulas are quite useful. So what we're saying here is, on the left hand side of that tilde we're saying the dependent variable, on the right hand side we're seeing the independent variable, and all this is saying here is speed. The tilde, we could read that as a function of distance, something like that. And then there's a comma, and then we're specifying what data we want to use. So what I've done, we could just run the syntax LM, our linear model, the dependent and independent variables in the model formula, and then data equals cars. What I've done here is I've saved it as a specific, if we ran that it gives us some printout, but I've saved it as a particular object. So let's run this. I'm going to highlight it and then we can run it. Let's run that particular line. So you can see in our environment here, it's created this new model with 12 list of 12 kind of 12 attributes, I suppose we could say. They're the different coefficients it contains. So if we actually call that object, if we just enter mod1, it will return some really basic coefficient information about the model, which is the intercept and the slope coefficient, the beta coefficient that is associated with our independent variable. Okay, so the slope, I didn't mention it previously. I'm assuming in many cases people are going to have some understanding of the equation for a straight line. But if we look at these values in the environment here, 8.2839, if we round that to two places, 8.28, and distance, the coefficient for distance is 0.1656. So if we round that to 2, that'd be 0.17. Let me change that here above. So the equation for a straight line would tell us the relationship between these two variables, if we modelled them with the straight line, our speed would be equal to the intercept value, and this is the value where our regression line crosses the vertical or y-axis. If we entered a value of 0 here for the distance, okay, if we entered 0 for the distance, this would become 0, this multiplication here, and all we'd have is the intercept value. Okay, so our intercept's 8.28 plus 0.17, that's our coefficient here, rounded to two decimal places, rounded up, times whatever we enter for the distance, so whatever value we put in for distance. So that's telling us the straight line relationship between our variables, and that's useful to know. That's the sort of thing we would report if we were running this type of model to analyze some data, but usually we want a little bit more than that. So a kind of a more useful call is the summary function, and then we pass our model object to it. That gives us more information. It gives us kind of more things that we would need or want to report for this analysis. So if I do summary and then pass in our model 1, you can see below that it's given us a lot more information. So it's shown us our call, our formula, speed as a function of distance, and the data we've used. And then it's given us residuals, mean, first quartile, median, third quartile, maximum. But then it's also given us our coefficients again. So the intercept, 8.28, the coefficient, the slope associated with our independent variable, 0.165, 0.17 if we round that. It's also given us standard errors and some significance tests with regards to those coefficients to tell us whether they are significant. So you can see here we've got a t-value, an associated p-value, which is probability, which is extremely small. So what this is telling us is this is kind of like a distance here, given this slope, is a significant predictor of our dependent variable speed. Okay, and then underneath we've got some more useful information here. We have got so we've got some residual standard errors, degrees of freedom, things like that. But we've got R squared values, which are kind of useful. So the one we probably want to report is the adjusted R squared. That's kind of taking into account issues with the data. And it's returning a value of 0.643. So what this is telling us was roughly about 64% of the variance in speed can be accounted for by braking distance. So as we know, because this was significant, distance seems to be a pretty good model, and it doesn't account for all the difference in all the things that might affect the speed of the car, but it's accounting for a lot of the variability. It's explaining a lot. This model is kind of a reasonably good model. Let me go up a little bit. This model is a reasonably good model for this particular independent and dependent variable that we've fitted. All right, so that's one way to do it. I've created a model object. We've passed it to the summary, but I thought I'd demonstrate the other way. You've seen me do this a few times previously, but what I'm doing here is I'm just using the pipe operator to kind of that. I've said previously that this, the pipe operator, the functionality you're getting off from the tidyverse is pretty good in that sense that it kind of allows you to sort of logically specify your arguments in a certain order. So first of all, we specify the data we want to use, cars, then we pipe that, and then we want to fit a linear model with speed as our dependent variable, distance as our stopping distance being our independent variable. And note here that I've also had to include data equals, and then I've just put a full stop or a period, just a dot. Okay. So usually, when you pipe things, you kind of specify your data first, and then you don't have to specify it again. But when we're using these statistical formulas, we saw a similar sort of thing with the t-test and with ANOVA. The way they're set up, they're expecting the formula and then the data. So this is kind of a way to kind of tell the model specification, or this LM function, that the data we want to use has been specified previously when we said cars. And then I'm piping that into the summary function. So if we run all these, we're fitting exactly the same model again. It's just a different way to do it. Depends on kind of your preference. But you'll see there we get exactly the same result as before. Okay, so quite useful. So what we've got here is a significant model, essentially. So what we're seeing is that speed can be predicted by, if we could measure the stopping distance, such as maybe the skid marks of a vehicle, we'd be able to predict roughly. We'd be able to predict its speed with kind of fairly reasonable accuracy, looking at the way we've kind of set up this particular model. Anyway, so it's useful to visualize as well. So what I thought I would do is I'm not going to use ggplot, so it's going to be a really basic plot that we'll create here. It's just the kind of base plotting function from R that I'm going to use. And we're going to kind of create a scatter plot of our two variables, distance and speed. And then I'm going to fit that regression line to it. So this first line here, we're going to create a scatter plot for distance from the car's data set on the x-axis, speed on the y-axis. X labels distance, Y label is speed. And then I'm going to run both these lines together. Then the argument I'm going to use AB line, AB line. And within that, within parentheses for that function, I'm passing our entire linear model specification, LM specification. And I'm also saying make the color of that line. So we're going to create a scatter plot of our data and fit the regression line over the top. So like I said, it's pretty basic, but it gives you a reasonably good impression. So you can see what the data looks like roughly. It's not exactly linear. There are errors, obviously. There are always going to be. There's going to be noise in data, but this kind of line, this regression line, you could think of it like a best fit line. Where's the best place to put the straight line to try capture that pattern of data? Does a reasonably good job of capturing that relationship. And the slope of this line is the coefficient we got for our independent variable at 0.16557 and our intercept 8.28. You can see it's going to be where this red line meets the y-axis, so it's roughly about there on that particular plot. Okay, so that is very simply a very simple linear regression model, how to fit it, different ways to specify the formula, and just a kind of visual check using a plot just to see that it all looks correct and makes sense. In the next video, I think I'll do some multiple regression, so we're going to add further independent variables to make a model more complex. But all we do there is add terms, so they'll each get a slope in relation to the dependent variable. Okay, so that's it for now. Hopefully this was useful. Thanks for watching and listening, and I'll record another video soon.